Let's continue that example that we started in the previous video. There it was problem 9.18a from the textbook, and we had used the Bode method to draw the magnitude response. Now, in the past, I've used l08 to come up with the magnitude response when we had the circuit. Here we weren't given the circuit. Instead, we were given a mathematical expression for the transfer function. So in that case, it's a easier actually to use Octave or MATLAB to get the draw the magnitude response and phase response as well, for that matter. So the way we can do that, and I have this MATLAB Octave script here. It's PR019_18a.m, and this will be available for download on the course website, so under the lectures link. So I encourage you to download this and then run it yourself, either in Octave or MATLAB. And it's really easy to create these magnitude responses in Octave. So the first thing I do is create a frequency vector that contains all the frequencies at which I want to evaluate the frequency response. And so here I just use the log space function to do that. And what it's going to do in this case is create a vector that has 500 elements that are equally logarithmically spaced between 10 to the 0 and 10 to the 4th. So that would be between 1 and 10,000. And that's the same frequency range I used when I was manually drawing the response. I chose to use that same frequency range here. You know, you could use fewer points or more points than 500. That's somewhat arbitrary. I just chose enough to get a smooth looking graph. And then now my frequency response is almost identical to the way it was in the textbook. You don't have to put it in standard form or anything like that. We could have entered it in their factored standard form, but it's 30 times 10 plus j times my frequency vector. Now I use the element by element operations here because I'm dealing with vectors. So I want to use dot slash instead of slash. Otherwise, it will try to do matrix division, or rather multiply this by the matrix inverse of the term to the right. So it's dot slash, and in the denominator I've got parentheses surrounding the two terms, 200 plus j times 2 times omega, and again this would be another vector that's then multiplied by this third vector, the two pole terms, dot asterisk, because I'm using element by element multiplication of these two terms. And then the last pole term is 1000 plus j times 2 times omega. So or W. So almost exactly how the response was given in the problem. And then here in the next, so H here would be a complex vector consisting of 500 points. I take the absolute value of that, so that would take the square root of the sum of the squares of each of those complex values and return the magnitude. And then I use 20 times log 10 of that to get the magnitude response in dB. Now be careful in Octave or MATLAB, log is actually the natural log. So on most of your calculators, the natural log is ln. But in Octave, log is actually the natural log, and you have to use log 10 to get the log base 10 of a vector. So, and I could have actually written this in one line, just 20 log 10 of absolute value of h, but I separated out the linear magnitude response and then the response in dB. And the rest of this is actually just plotting. Notice that instead of using plot, W versus the magnitude response in dB, I use similog x, so it'll be more similar to our hand-drawn plot. And I rescale the y-axis, so it actually has the same vertical scale are similar to the same vertical scale as our hand-drawn plot. So again, just really a couple of lines here to get the magnitude response, and then actually more lines to plot the response than to actually get the vector containing the magnitude response. So I run this. Let me pull up, and the plot looks like this. Okay, now let me pull up my plot in dB, pull these side by side, and I guess maybe depending on your point of view, they look pretty similar or not. You know, notice if I over here in an octave plot, if I move my cursor around, you can't actually see my cursor in the video, but I've got it right on the left edge of my blue plot. You'll see down here at the bottom, when I do that, you know, it shows minus 56 dB, minus 56.3 dB. Let me move it to the peak response here, and I see it changes, which is at, you know, 220 some radians per second. Let me move it to like 200. It's at a minus 37 dB. So again, moving over to my hand-drawn plot, you can see it corresponds pretty well here. We said that, you know, it was minus 56.5 dB at the left. You know, it has a peak response here of about 36.5. Let me go back over to the paint program and choose to draw the pencil. Again, let me get this same blue curve. Remember, I said there would be a little correction here of about 3 dB. You know, when we're drawing these. So if I smooth out the knees here, I know the response is going to look something like this. And then here it's going to be smoothed out like that, and smoothed out again over here. I'm not doing a great job here. And then asymptotically, you know, approach the line there. So, you know, with the smoothing at the corners, it's going to look very much like the response I get in octave. So again, this Bode technique gives us a quick and easy method to come up with the magnitude response of a circuit, or in this case, we actually started with the magnitude response and then drew the Bode plot from there. I'm going to stop the video here, and we'll come back and do one more example.